G'day, folks.
Okay.
It's a long way from down under, so really glad I could join you today, even virtually through the video and then online through Q&A shortly. My name's Gavin. I've, I guess, been involved with a lot of the sustainability issues and environmental issues around mining now for close to 25 years. And a lot of the work I do really comes from and is inspired by a lot of community concern, thinking about, what do we mine, where do we mine, how do we mine, and often why do we mine as well. And so again, each of these photos tell, I suppose, different elements of that story, but again, hopefully they make you think a bit too. Hewitt first published, I guess, a very seminal paper in 1929 and thinking about, well, the rise and fall of mining. And in many ways, he was looking at Europe as an example of where mining used to be prolific and had sort of really shifted to North America. And then different parts of North America really declined as well. And so he basically documented that and looked at that rise and fall and really started thinking about peak metals and what that means for the ongoing supply. And so basically, of course, mining shifts around. And Hewitt, of course, was a mentor of Marion King Hubbert, or the father of peak oil. And so although a lot of people think that peak oil was really invented by Hubbert, it was actually, peak resources was really invented by Hewitt. Right, and again, you could go back probably to before that time to Roman and Greek times as well. But I guess in the modern context, Hewitt was the first person that really looked at modern mining and started thinking through these things and looked at the evidence. Now, if we look at mining, I guess there's the modern mining world. Yes, it gives us a lot of the metals and minerals and energy that we need. For a whole bunch of things, whether it's really simple materials like cement and steel, through to complex technologies such as mobile phones and laptops. And really, there's two schools of thought. One says that there's only so much metal or mineral on the planet, and that's it. That once we've mined them all, they're gone. That's it. It's unsustainable. And then the economists would chip in and go, no, we can always find higher cost resources, and technology can be developed. And so really, we're never going to run out. It's just a matter of pricing. And again, I think the economists look backwards and say, well, look, Riverway's been proven right. And fixed stock people look forward and go, well, eventually we'll be proven right. And so really, at the end of the day, you've got these sort of two theories. But in the meantime, of course, we live in a world where we are committed to sustainable development. The mining industry globally has been committing to that since the Johannesburg Earth Summit in 2002. But at the same time, how do we get more sustainability performance out of the industry when we've got declining ore grades, more difficult ores such as arsenic-rich or mercury-rich ores? We've got more mine waste, tailings and waste rock to manage. We've got regulatory compliance we have to be concerned about, the governance at a corporate level. But also, how do we deal with climate change? Both the risks to mining from climate change, but then how does mining contribute to climate change as well? Both mitigation and adaptation and everything else. And so all of that's within a milieu of rapidly changing market demands, community expectations, but increasingly investor scrutiny, right, financier scrutiny. And so that's the grand challenge. Now, of course, I won't go through this in great detail, but really it's about mining is finding more deposits, how we mine them, open cut, underground, how much waste rock, and all of these types of things, right? And so really, over the last century or so, we've seen mining increase in scale at an individual level, right? And so instead of lots of small mines, we now have a handful of really big mines, right? And so that means that it leaves more waste, it requires more energy, releases more carbon, right? And so really, that's what we need to think about is what we mine, lithium or uranium perhaps, right? I would certainly argue lithium, but then, where we mine. Antarctica is an area we shouldn't be touching, I would say, as one example, right? But then when we're looking at some other things, it's like, well, how we mine. Should we be mining through open cut or underground and so on? And really, there's very few studies of these types of things at the global level. And so that's, I guess, where a lot of my research has been focused now for some time, is how do we look at these types of questions at the global level? So let's look at copper, and we can see this is the resources that we put together for the year 2015. And this is with my colleague Simon Jowett. And so we look at the higher grade, you can see, they're the much smaller deposits. As your grade declines, you get to the giant copper deposits, the porphyries. And then as you go down the grade curve, you get to your magmatic sulfides, which is where copper becomes a byproduct, not a primary product. All right. Now, if you look at Skinner, he first proposed that you have this bimodal distribution for mineral deposits back in the 1970s. And really that our current mining is these enriched geological zones or mineral deposits, right? And they're unique. They're different to average crustal rock. And the switch from our enriched zones to average crustal rock is that mineralogical barrier, where you're moving from sulfides or easily smelted oxides and leached oxides through to aluminosilicates and so on, where you're dealing with substitute elements, not primary minerals, right? And so I guess our work is really the first empirical evidence that really suggests that that Skinner was certainly right. So if we look at manganese nodules, for example, as one type of resource of the future, potentially, certainly some argue that, we can see that, of course, the grade is decent, the size is certainly big, but there's a lot more to it than that. It's the biodiversity issues, it's the energy costs, and all sorts of other things as well. We know the grades are always declining, and this is some really long-term data sets I've been able to build to look at different countries around the world. And so we can see that really the only long-term trend obvious here is long-term decline. And there's a bit of rise and fall in different countries, such as Australia or Canada and Laos and others. But fundamentally, the long-term decline is really clear and obvious here. All right. And so what that means, of course, is that that decline means more energy and more waste left behind. If we look at global nickel, we can see the sort of the rise and fall of different countries over time on the top right here. We can see that in many ways, Canada, it looks like it's being squeezed out of the market, but when you look at it in tonnage terms, it's still pretty constant. All right, so it's certainly far from sort of peak nickel in Canada. But the bigger picture here really is understanding the types of resources that we're mining for nickel. And although you've saw sulfides in Europe on small scale, then the switch to laterites with New Caledonia, and then the dominance of nickel sulfides thanks to Sudbury in Canada. Since the sort of the mid-20th century, we've seen this gradual shift back to laterites again. And laterites are much, much more energy intensive, right? And so they're more abundant. About 70% or so of global nickel resources are in laterites as opposed to sulfides. All right, and we can see that here. And you've got your mineral resources on the top here, ore reserves on the bottom. And on the left column, we've got our ore grades and contained nickel. And then on the right-hand side, we've got unit ore value, which accounts for all the co-products and byproducts. So with nickel laterites, you can often have cobalt. With nickel sulfides, you often have copper, platinum group elements, and cobalt. All right, and so looking at the different deposit types, we can see that laterites are typically higher grade in nickel, but once you account for byproducts and co-products, the value all evens out a lot more. All right, and so that's I suppose that gives you an insight into the differences there. But we know that in terms of sulfides, grades are on average declining. Tiny, in some ways, a very gradual increase in Canada, and certainly this increase in the last 15 years is due to the Voisey's Bay project being developed. So new deposits can actually help increase grade, but we're still well below the earlier grades, say a century before that in Sudbury. For nickel laterites, it's a very simple case. It's just all downhill. Right, and so there's really no argument around the grade decline in nickel laterites. It's just all declining very gradually. Right, which of course has a lot of significance. When you're looking at these sorts of issues globally, again, this is just looking at global production data and the global reserves as reported by the USGS or previously the US Bureau of Mines, and then mapping it out on a periodic table. And all of these elements still show significantly increasing cumulative production over time, perhaps with the exception of mercury, which is much more environmentally constrained, certainly not resource constrained. All right, we can see our rare earths here. So the yellow shows that we've still got substantial resources known, or reserves, I should say, known for almost every metal. Now, life cycle assessment is something we'll be hearing about today during the think tank, but I just need to frame this in terms of looking at mining, because as we go down in grade, of course, that means our energy cost goes up and our carbon cost goes up. All right, and this is from some work done at CSIRO here in Australia. Looking at developing sort of, I suppose, some models of different ways of producing, in this case, copper, right? But very similar models you could that have been developed for nickel and so on and others. So if you look at what's actually reported by mining companies in terms of their carbon costs and so on, and again we can see the variability depending on the configuration of the mine, but that broad trend is obvious. As grades decline, that cost starts to go up. All right, and we can see the same with uranium. And so if you look at the specific projects over time, we can see these increases over time as well. All right. Now, what we do about that, I guess, is the really important question. Do we go through mechanization that maybe increases the energy cost? Do we come up with new technologies that decrease the energy cost? As we move from the higher grade resources and we deplete the higher grade, we move to lower grade. How important are economies of scale in actually going this way, or perhaps there's really economies of scale going to the left here? All right, and certainly how does deep sea mining fit into that? And I think at the moment, of course, we have no operating deep sea mines, so a lot of the LCA sort of studies that have been published to date, of the few of them, are still very theoretical and so on. We don't really have, I guess, a lot of operating data to validate that. So just quickly, we look at changing metal demands, and we know that global nickel is scheduled to expected to increase substantially in coming decades to meet things such as our transition to renewable energy and electric vehicles. And so just the demands for battery metals alone, we can see on the right here, depending on the sort of scenario that we choose, like the sustainable development scenario from the International Energy Agency or the new policy scenario. And so nickel starts to take up, just for batteries, is a huge fraction of expected global nickel demand. Right, and so that's a big change from what we've seen, where stainless steel is pretty much the dominant dominant metal demand for nickel. So overall, we don't have a shortage of resources. We really don't. What we do have, I guess, is a shortage of understanding what the environmental and, I guess, social consequences of that metal mining is. And at the same time, of course, we're building in mining with declining grade, so we're increasing that energy and carbon cost. At the same time, the world is trying to achieve some really significant progress on issues such as climate change and decarbonisation. So there's a variety of different solutions, but I guess we have a long way to go before we find out and really validate, I guess, which ones are the best ones to help do that. And that may be the electrification of mining, looking at the ways that we mine, the renewable energy supplies to mining, and so on, and the types of resources that we mine. Right? But I think at the moment, I don't think we have any really good answers to that yet. We're all still working on them. But we'll leave it there. Thank you.